Hello everyone, I am Leo and I will be presenting our work titled Emulating Goliath Storage Devices with David today. This is joint work with Nitin Agrawal, who graduated with a PhD a year ago and is now with NEC Labs. And we were guided by Andrea and Remzi Arpaci-Dusseau. Let me start my talk with the storage researcher's dilemma. Researchers innovate the future. For many years at FAST, this research community has been coming up with interesting ideas to build newer, faster, and better file and storage systems. Once we have an innovative idea, the next step is to measure and quantify the improvement that this new storage device provides when compared to the state of the art. Thus, the dilemma. How does one measure a better performing storage device from the future when all that he or she has in hand are devices from the present, or worse yet, from the past? We present David, a storage emulator that allows one to emulate large, fast, and multiple disks using a small, slow, single device. One can emulate huge disks and multiple disks with David. For example, we were able to emulate a storage disk of size approximately 1 terabyte using a 80 GB hard disk. We were also able to emulate multiple disks using RAM and able to run RAID on top of these emulated disks. How do we do this? The key idea behind David is to store metadata, throw away data, and to generate fake content when needed. This is okay because most of the benchmarks are written to measure the performance of storage devices. They often don't care about the file content that they store or retrieve on the storage device. Popular file system benchmarks like the Postmark and FileBench fall under this category. Some benchmarks, like VirusScan, expect valid content but not exact content. We take advantage of this observation to build David. Here is the outline for the rest of my talk. I just introduced David. I'll go over an overview of how David works in the next few slides. Followed by that, I'll be presenting the design and implementation details of David. Later, I'll show you evaluation results. And finally, conclude. Here is how a typical benchmarking setup looks. The benchmarking application runs in the user space and issues file system calls. The file system, in response to the file system calls issued by the benchmark, creates a bunch of disk I/O requests and sends it to the disk drive. David is written as a pseudo block device driver that sits right below the file system and intercepts on the disk requests generated by the file system. David uses a storage model to mimic the performance of a real device. It uses a backing store to store the metadata. Let us consider an illustrative benchmark that creates a file, writes a block of data, closes the file, reopens the file in read mode, and reads back the data it just wrote. And consider how David handles the stream of I/O requests that this simple benchmark generates. The benchmark here creates a file in write mode, and the file system allocates an inode, let's say in block 100. The file system tries to persist the inode information on disk by issuing a write to the inode block at logical block address 100. David intercepts this write to metadata and uses a storage model to calculate the response time for this write request. Since this is a metadata block, David remaps this write request to an available slot in the backing store, in this example, logical block address 1, and persists it in the backing store. David also maintains a remap entry with enough information about the remap that it just did. Finally, a response is issued back to the file system after a delay calculated by the storage model. Now the benchmark tries to write a block of data to the file. The file system issues a write request to data block at logical block address 800. David intercepts the write to the data block and uses the storage model to calculate the response time for the write request. Since this is a data block, David decides not to throw it in the backing store, not to store it in the backing store, but to throw it away. Finally, a response is given to the file system after the delay calculated by the storage model. In this simple example, since we store just one of the two write requests, we achieve a space savings of 50%. Let us consider what happens when the benchmark tries to read the file that it just created. The file system tries to read the inode block. David intercepts the metadata read request and uses the storage model to calculate the response time for the request and consults the remap table to figure out where in the backing store was this logical block address 100 remapped earlier, fetches the data from logical block address 1, and returns back to the file system after a delay calculated by the storage model. Finally, the benchmark tries to read the data block that it created earlier, and the file system issues a read to the data block at logical block address 800. David intercepts this read request, uses a storage model to calculate the response time, and since this is a data block, David just fills the read request with fake content. Finally, a response is issued back to the file system after the delay calculated by the storage model. Here's the outline for the rest of my talk. I'll talk about the design and implementation details of David now. Here are the design goals that we had in mind when we started developing David. David needs to be accurate. A storage systems researcher should be able to emulate a disk using David and run benchmarks to get runtimes that are very similar to the runtimes he would have got had he run the benchmarks on a real storage device. David needs to be scalable so that one can use it to emulate large storage devices with minimal storage space. We wanted David to be lightweight so that the emulation overhead itself does not affect the benchmark performance and lead to inaccurate benchmark runtimes. David should be flexible enough for one to emulate a variety of storage disks. Finally, we wanted David to be adoptable so that it's easy to install and use for benchmarking purposes by storage researchers. This slide shows the components that David is made of. The block classifier helps David in classifying metadata blocks from data blocks. The storage model is used to mimic the performance of a real disk device. The metadata remapper remaps the metadata writes and lays them out efficiently on the backing store. The data squasher squashes writes to data blocks, and the data generator generates fake content for data read requests. I'll go over the details of all these components in the next few slides. Right now, I'll talk about the block classifier in more detail. Block classification is the process of generating information that David can use to distinguish data blocks from metadata blocks, and then throw away the data blocks and store the metadata blocks. This is a difficult job because David is implemented as a block level emulator, and all that it sees is a stream of write requests. There are two approaches for block classification. The first is called implicit block classification, wherein David automatically infers the classification information by observing the metadata writes. The second approach is called explicit block classification, wherein the operating system is modified to collect and pass down classification information to David. Let me talk about the implicit block classification in more detail now. In this approach, David tries to parse the writes to metadata blocks and uses the file system knowledge to infer data blocks. We implemented this approach for the ext3 file system. ext3 lays out inode blocks in a specific range of logical block addresses. David uses this information to identify inode blocks. Once inode blocks are identified, David intercepts writes to inode blocks and parses it to obtain information about direct and indirect blocks. And once this information is available, David parses writes to direct and indirect blocks to infer the data blocks. All other blocks are considered metadata. There is a problem with this approach, which is the delay in classification. To understand this problem further, let's understand how writes are issued in ext3 ordered journaling mode. In this example, the metadata blocks are colored blue and the data blocks are colored red. The file system writes the data blocks initially to the on-disk location and checkpoint and commits the metadata blocks to the journal, and finally, after a delay, it checkpoints the metadata to the on-disk location. Let's see how David handles this stream of blocks. With David around, when the file system writes the data blocks to the on-disk location, David doesn't have classification information yet, and hence stores this unclassified block in the unclassified block store, which is in memory. This happens with the next couple of data blocks too. Finally, the file system writes the metadata to the journal and then writes the metadata to the on-disk location. This is when normally David parses the metadata blocks and obtains classification information, and then uses the classification information to process the unclassified blocks in the unclassified block store. However, too many unclassified blocks can end up being stored in this unclassified block store, and this can exhaust the memory resources in a system. In a data write intensive workload, there can be too many data writes in a short period of time before the corresponding metadata block is written, and hence cause too much memory consumption. To handle this, we use a technique called journal snooping, wherein we parse metadata writes to the journal to infer classification information much earlier than usual. Here is a graph that shows the memory usage with and without journal snooping. The x-axis is time in seconds, and the y-axis is memory used for a typical benchmark. The blue line shows the memory consumption without journal snooping, which is in the order of hundreds of megabytes. And as you can see, the system can go into out of memory state for some workloads. With journal snooping, however, the memory resources needed are less than 100 MB, and this works cool. Let me now discuss the details of the second block classification approach, which is the explicit block classification. The key observation here is that all the data blocks are generated by the benchmarking application. However, the metadata blocks originate from the file system. Hence, the idea here is to capture the page pointers to data blocks at the operating system write system call interface, and let the operating system pass this list of page pointers to David for use during classification. When David receives a write request, David checks the page pointer in the list provided by the operating system, and presence indicates data block, absence indicates metadata block. This slide shows a summary of the two different block classification approaches that we just discussed. Implicit block classification approach doesn't need any change to the file system, the benchmark, or the operating system. However, it needs file system knowledge to parse the metadata. The explicit block classification approach, on the other hand, needs minimal change to the operating system, and since it doesn't need file system knowledge, it works well for all file systems. We have implemented implicit block classification for ext3, and I'll show the results in a few slides. And explicit block classification approach was tested with btrfs. Let me now talk about the storage model within David. In an actual system, the I/O request queue and the disk drive sit below the file system. Since David is written as a pseudo block device driver that sits right below the file system, David should model both the I/O request queue and the disk as part of its storage model. This slide shows some interesting properties of the Linux I/O request queue that David has modeled. Sequential I/O requests are often merged into a single request before sending it to the disk to improve performance. When the I/O request queue is empty and a new request arrives, that request is made to wait for 3 milliseconds, anticipating merges with future I/O requests. When the I/O request queue is full and a process tries to enqueue I/O request, the process is made to sleep and wait until an empty slot opens up on the I/O request queue. However, when the process is woken up, it's given permission to enqueue a constant number of requests in future, even if the I/O request queue is full, as a bonus for the wait period that it just went through. We have modeled all these interesting properties in David, and they are very critical for accurate emulation. More details are in the paper. We have a very simple disk model, which is based on the Rumler and Wilks disk model. Currently, we have modeled a 80 GB and a 1 terabyte Hitachi Deskstar disks. Our disk models are accurate enough for emulation purposes, but they are not perfect. To evaluate the accuracy of David's storage model, we ran several benchmarks on top of the storage model and plotted cumulative distribution frequency graphs and calculated the demerit numbers. This graph here is from one such workload. This is not so well. We had much better workloads. The y-axis is the fraction of I/O requests that got completed in the time that the x-axis specifies. More results on the accuracy of storage model are in the paper. Let me now discuss the metadata remapper and the backing store components of David. David uses the backing store as a storage space for metadata blocks. Any storage can be used as a backing store as long as it satisfies two conditions. The first is that it must be large enough to hold all the metadata blocks generated by the given benchmarking workload. And the second condition is that it must be fast enough to service metadata read requests when compared to the times that the storage model emulates for such requests. We have two implementations of backing stores. The first implementation is to use memory as the backing store, which is obviously faster than any normal storage device and hence ideal for emulating even solid-state storage devices. The second implementation that we did was to use a magnetic disk but lay out metadata in a compressed format, thus obtaining a compressed disk. Let me talk about the compressed disk further here. The metadata remapper remaps metadata blocks and lays them out sequentially on the disk. Since the inode blocks and metadata blocks are laid out sequentially, the service times for metadata reads are much faster, and this allows David to emulate faster storage devices. Let me now discuss the data squasher and data generator components. The data squasher throws away writes to the data blocks, and the data generator generates fake content. Currently, we just generate random content. More interesting data generation techniques are possible. Let me now discuss the evaluation results. We conducted 3 sets of experiments. The first set of experiments tried to measure the accuracy of emulation with David. The second set of experiments test David's scalability in emulating large storage devices. The third set of experiments test David's ability to emulate multiple disks. For the accuracy experiments, we emulated a 1 terabyte storage disk with a 80 GB disk. We ran a variety of benchmarks, and we validated the results against a real 1 terabyte disk. This graph here shows David's accuracy with ext3 in the implicit block classification mode. The blue bars are the real times, and the red bars indicated the benchmark runtimes on an emulated disk. This bar graph here shows David's accuracy when run in the explicit block classification mode using btrfs. As seen from these two graphs, David's accuracy is pretty good for benchmarking purposes. For the scale experiment, we emulated a disk of approximately 1 terabyte size using an 80 GB disk, and we created file system images of varying sizes from 10 GB up till 800 GB using the impressions tool. Again, these results are validated against a real disk. This graph here shows that David is able to accurately emulate large storage devices. The runtimes that are predicted and the actual runtimes match very closely. This graph shows the storage space savings with David, and David is able to emulate up till 800 GB for the impressions workload with just 10 GB storage space. For the multiple disk experiment, we emulated lots of devices using RAM as the backing storage, and we ran micro benchmarks on top of RAID. Again, we validated our results against real disks. This graph here shows random read and random write workloads. The x-axis shows R stands for random reads and W for random writes, and 3 for 3 disks, 2 for 2 disks. Again, the runtimes of the emulated disks and the actual disks match very closely. To conclude, we presented David, which allows one to emulate large storage devices with limited resources. The key idea we used is to throw away data. We also showed experimentally that David is able to emulate large and multiple disks accurately. In future, we want to extend the limits of scalability with David by emulating lots of storage devices and try emulating storage clusters with fewer machines. Thank you. I'll now take questions.
Jeff Canning, Harvey Mudd College. Your explicit classification system works on the assumption that any block written by the file system is a metadata block. But it seems to me that in journaling file systems, in their full journaling mode, they are writing data blocks to the journal, and this won't work.
Yep. I guess we'll have to add more information. Like in that case, it will be a combination of not using file system information and using information about the file system to classify. I don't have specific answer.
Vasily Tarasov, Stony Brook University. So you have implemented David at the level right below the file system. So as a result, you needed to emulate all this fancy behavior of Linux, I/O scheduling. And Linux has multiple schedulers, so it looks like this functionality also needs to be incorporated in David. So we're thinking about moving David to one level below to driver level, for example. It looks for me like you still have all needed information to implement it there.
Yep. That's an alternative way to do it, but the advantage of having David sit right below the file system and above the IO request queue is that there is a possibility for speeding up the benchmarking process. So if David sits below the IO request queue, then there is the queuing effect of the IO request queue, which is not modeled, but which David has to deal with because the queue is above it. And so the wait times of requests cannot be modeled. So implementing David in this way gives us an opportunity to try out speed up modes where actually the benchmark runs really quickly and outputs the actual emulated runtime. Yep.
Okay, so it looks for me that in this case you need to position your system as emulation of both storage and OS IO scheduling.
Yep.
Thank you.
How would you deal with the false negatives in your implicit classifier? Like if you classify a metadata node as a data node and you don't actually store it?
We try very hard that we never do that. Yep. Classifying data as metadata is fine. We are just losing some storage space. Right. But classifying metadata as data is critical and we just crash. And that never happens with ext3, so we spent a lot of time making sure that doesn't happen.
Have you looked at file systems that separate metadata from data? I have one of those, so I was thinking that could be an easier way to use your simulation in such a file system, because you can always look at the partition, which is also metadata independently. Did you look at such a thing?
Yep, that's, if a file system is able to provide the classification information, like in some format, if it's partitioning, yep, that's ideal, and it'd be so easy to.
So maybe we can talk about that, because I didn't finish the work on the dual FS, but
Okay.
that's very suitable for this to use it for simulator. It's perfect, because you have one disk does metadata, another disk, so you know exactly what data is.
I'll catch up with you after the talk. Yeah.
Yeah, hi, Nitin from Recipient. What happens if you, it is possible that some of the IOs you may not see because, reads, for example, you may not see because the file system has already cached some of the inodes and the block map, and it starts reading data blocks belonging to those inodes and block maps. And you had seen these reads long time ago, but now you have not, and then it starts reading these data blocks. How do you know that these are data blocks it's trying to read, and you should generate the data?
So in the explicit
mismatch between your cache and the file system cache, right? File system caching a lot of stuff.
Yep, this problem occurs with the implicit classification approach.
Yeah.
And the unclassified block store actually is used. So we don't throw away blocks in the unclassified block store unless we are sure that it's data or metadata. And in case so the file system wrote some data and we didn't know to some block address, and we don't know whether it's data or metadata, we keep it aside. And then if there is a read to the same address later point of time, we just fetch it and give it from the unclassified block store.
Okay.
Yep. I can.
Again later.
Yeah, sure. Thanks.